Welcome everyone to our Novo Nordisk Network for Healthy Populations virtual seminar series. Thank you so much everyone for joining us. Please let me know if you can't hear or you're having any problems. I think my volume is okay. So I'm going to, before I introduce our speakers today, I'm going to start with a land acknowledgement. So I would like to start by acknowledging that I'm coming to you from Toronto, which is covered by Treaty 13. But the Novo Nordisk Network for Healthy Populations is situated on the land on which the region of Peel operates, which is part of the treaty lands and the territories of the Mississaugas of the Credit. And for thousands of years, Indigenous peoples inhabited and cared for this land. And in particular, we acknowledge the territory of the Anishinaabe, the Huron-Wendat, the Haudenosaunee, and the Ojibwe Chippewa peoples, as well as the land that is home to the Métis, and most recently, the territory of the Mississaugas of the Credit First Nation, who are direct descendants of the Mississaugas of the Credit. And we are grateful to have the opportunity to work on this land, and by doing so, we give respect to our first inhabitants. So welcome everybody, and thank you for attending today's Network for Healthy Populations Banting and Best Diabetes Center joint clinical and population research and progress rounds. It's a big mouthful, but that's the name of the seminar series today. And we're really pleased to have presenting their research in progress two graduate students, Ingrid Geisinger and Scarlett Rakowska. Before I introduce you to the students, I just want to quickly review some housekeeping items. We appreciate our audience muting themselves during the presentation. We will be having each presenter will present for about 20 minutes, and then we will have an opportunity for a Q&A period at the end of each session. We have the supervisors of each student as well as faculty advisors that have been identified by the students as folks that they would like to get some feedback as well. And we will be asking the faculty advisors for each student to lead the Q&A period after their talks. But others will have an opportunity to ask questions. You can either use the raise hand function or use the chat box for your questions. Lastly, please note that today's session is being recorded, and we will be making the recording available on the network's website. So now I'd like to introduce to our first speaker today. Ingrid Geisinger is a doctoral student under supervision of Dr. Laura Rosella. And Ingrid's faculty advisor for this session today is Dr. Arjuman Siddiqui. Ingrid is a fourth-year doctoral student in epidemiology at the Dalla Lana School of Public Health at the University of Toronto. She has extensive experience as a statistician with the British Civil Service and as a research scientist with the World Trade Center Health Registry at the New York City Department of Health. She holds a BSc in Natural Sciences from the University of Calgary, as well as a B.Ed from the Ontario Institute for Studies in Education at the University of Toronto. She also holds a Master's of Science in Health and Society, Social Epidemiology from the University College London. Ingrid is utilizing unsupervised machine learning methods in her PhD research to develop a theoretically informed social risk measure and evaluate the effect of social risk clustering on multimorbidity in Ontario. I think I'm going to hold the introduction of the second speaker until she speaks, just so that it's fresh in people's mind. So I am going to actually pass it on now to Ingrid to launch her presentation. So go ahead, Ingrid.
Right. I assume you can hear me, and hopefully you
Yes.
can now see my slides.
Absolutely, yes. Although there is, oh yes, perfect. They're perfect. Go ahead, Ingrid. Thank you.
Okay, wonderful. I'm just going to minimize that. Okay, I'm really excited to share my research to date with the group today. Before I begin, I just want to take a minute to add on to the opening words this afternoon to personally acknowledge the lands in which we're gathered. I'm here on the traditional ancestral lands of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. As a scientist and as an activist, it's important to me to take the steps to learn about the Indigenous peoples who lived on and tended to these territories since time immemorial. I would like to express my commitment to support the fight against the oppressive systems that have affected Indigenous peoples. This is vital for advancing human rights here and globally. This seems like an appropriate segue into my discussion today about the research of the cumulative effects of social disadvantage. Advancements in data linkage and machine learning methods provide an opportunity to advance the consideration of the complex synergistic effects of multiple social determinants of health and their association with multimorbidity. The framework for the social determinants of health formalize the discussion on how the conditions in which we live influence our lives. Often, these frameworks are used to inform the selection of our metrics we might consider when looking at social patterns in a health outcome, your occupation, income, education, among others. When we consider the social determinants of health in research, we typically consider a single social determinant as a risk factor for a specific condition. For example, income is associated with cardiovascular disease risk, diabetes is associated with lower education, and certain occupations have an increased COPD risk. But often, these chronic conditions share common upstream social risk factors. For example, low education is associated with increased risk of diabetes, cardiovascular outcomes, COPD, and lung cancer. Chronic disease research has evolved to consider the co-occurrence of multiple conditions within an individual, known as multimorbidity. Multimorbidity is associated with increased disability, reduced well-being, and a lower overall health-related quality of life. It places a substantial strain on the healthcare system and is estimated to account for 2/3 of total allocable healthcare costs in Ontario. In Ontario, the standardized prevalence has increased over time from 26.5% in 2003 to 30% in 2019 across sex, age, and area-based income. But multimorbidity is also a growing issue worldwide, with an increased prevalence observed across high, middle, and low-income countries. In addition to the growing prevalence, we're also observing an earlier age of onset. A UK study described a decreased prevalence or a decreased median age of onset from age 56 to 46 over a 15-year period. But this decrease was not felt equally across the population. Among the most deprived, the median age of onset was 8 years earlier compared to the least deprived. There is an increased prevalence of multimorbidity among those with low incomes, limited education, and in minority and marginalized populations. These social determinants influence the health of individuals and across populations in complex, interrelated ways. However, much of the existing literature still considers the risk of multimorbidity associated with a single individual social determinant, which I refer to as the single risk framework. The current single risk factor approach overlooks the influence of multiple social determinants within an individual, the totality of social exposure, and its influence on health. My research focuses on how we consider the social determinants in our research and to explore the totality of social exposure within an individual. The first part of my research is to capture total social risk for Ontarians, which I propose to do through both a simplistic additive approach and again using unsupervised machine learning methods. To understand the functionality of the total social risk measure I create, I've focused on the co-occurrence of multiple chronic conditions within an individual. I will do this by evaluating the effect of these social risk measures on the incidence of multimorbidity in Ontario. To do this, I will be using a population-based cohort of linked data for Ontarians. The base of the study population has been formed using 6 cycles of the Canadian Community Health Survey. This has been limited to Ontario residents aged 20 to 55, focusing on a working age population. This study population is linked to Ontario Health Administrative data at ICES to capture the occurrence of chronic conditions. To define multimorbidity, a specified list of eligible chronic conditions is required. There's no standard definition. I am focusing on conditions which are highly prevalent, have an observed social gradient, are potentially modifiable, have a significant impact on the individual, and correspond to chronic disease groups important for policymakers in Ontario. The conditions for my analysis include congestive heart failure, chronic obstructive pulmonary disease, diabetes, lung cancer, myocardial infarction, and stroke. These conditions all have validated algorithms for identification in administrative health data, and I will be using a definition of the presence of 2 or more of these conditions in my research. So as an overview, my research is aiming to quantify total social exposure using the CCHS study population, and then identify the association with incident multimorbidity. In my first objective, I derived 2 social exposure measures and then looked at the effect of these indicators on the incidence of multimorbidity in Ontario. Over the next few slides, I'll describe the indicators and our results from this first analysis. And all analysis that I present today will be sex stratified. So from the CCHS, I narrowed down a list of social determinants that are available, which are highlighted here and have been used in the generation of the risk measures to summarize total social risk. Each measure contrasted those experiencing the most social disadvantage to everyone else. Here, I'm sharing the proportion experienced social disadvantage across each indicator among females and males in my sample. This highlights the importance of considering the social determinants separately for each sex, given the observed differences among males and females, especially among measures such as work history or income, among several others like food insecurity. And the first method I used to summarize social risk is additive. In this approach, the multiple social determinants are collapsed into a continuous measure. This is done by first collapsing each social determinant into a binary measure where one reflects social disadvantage and 0 reflects the more advantage experience across each of these measures. These indicators are then simply summed together to create a summary score of social exposure. This is a simple and crude approach, and it assumes that each determinant carries equal weight, which is likely not true. To address this, the second method introduces simple weighting. In this approach, the binary indicators are summed within a domain. Each domain reflects an aspect of social risk, which was informed by the conceptual frameworks for the social determinants of health. These domains are then added together to generate a summary score such that each domain contributes equal weight to the overall social risk measure. To ease interpretation, the additive and weighted social risk measures were then categorized into 4 groups. Here I'm sharing results for the additive measure, but plots like this were also generated for the weighted measure. These radar charts plot the proportion experienced social disadvantage on the contributing social determinant groups on the CCHS by the additive social risk grouping. So to interpret this, the green in the outer ring shows the proportion of social disadvantage across group 4, which is the group that experienced the most social disadvantage. What I found particularly interesting about creating these plots is that the group experiencing the least social disadvantage is actually absent from the plot entirely, as the proportion shown in blue, group 1, experiencing the least social disadvantage, experienced a proportion of 0 across all of the characteristics presented here. There were no immigrants in group 1, there were no visible minorities, all were homeowners, which I paused to say that this was quite striking to me as I generated this measure. Now, the second part of my work focuses on applying the generated social risk measures to understand the association with multimorbidity. Here I'm sharing pretty simple proportion plots, which are contrasting the proportion of the sample population and the proportion with multimorbidity by these total social exposure group membership. And as we see in green, among both males and females, the individuals with the most social disadvantage experience disproportionate burden of multimorbidity. Next, I used a competing risk framework to evaluate the effect of a social risk measure on the incidence of multimorbidity. To create a pseudo-healthy cohort, I've excluded those who are diagnosed with any of the 6 conditions of interest prior to that CCHS interview or within 1 year after the interview, focusing on incident cases of multimorbidity. When we look at plots of cumulative incidence, we see in green, group 4 experiencing the most social disadvantage had a higher cumulative incidence of multimorbidity among both males and females. So females are on the top and males are on the bottom, and by looking at both the additive total social exposure and the weighted measure. When we look at survival models, there's an observed social gradient in the unadjusted models and models which adjust for hypertension. Here I'm showing the additive measure, but these results are also consistent among the weighted measure, which I'm now showing on the screen. I also adjusted for lifestyle risk factors, which include smoking, alcohol, physical activity, and BMI. There's some literature to indicate that these are on the causal path from social exposure to multimorbidity. However, as they are also commonly adjusted for in chronic disease research, we decided to adjust for these measures as well. So here I'm sharing the weighted total social exposure, so unadjusted, hypertension adjusted, and finally the additional lifestyle risk factors included on the bottom. And when adjusting for these lifestyle risk factors in the weighted social risk models, the social gradient is retained. And just to reiterate that these results are comparable among the additive approach as well. The simple additive and weighted additive approaches have demonstrated that the risk of multimorbidity with a summary, or have demonstrated the risk of multimorbidity with these summary measures of total social risk. But both of these approaches simply demonstrate that having more social disadvantage is worse, without understanding whether all social determinants contribute. Do multiple social determinants actually capture multiple social things, or can this be unpacked into a few key things? I'm going to share briefly on my second objective, which is currently underway. In this part of my research, I'm using the same CCHS-based study population, but now the linkage is expanded to include census data from the 2001, 2006, and 2011 census, and this is linked based on the census nearest to the time of the completion of the CCHS survey. Measures that are included in this expanded data set include measures such as proportion of the population unemployed, proportion of the population living alone, proportion of the dwellings in need of major repair. With the linked CCHS and census data, I have a comprehensive data set with over 40 measures of individual and area level social determinants. This linked data set includes a vast number of variables, many of which are interrelated. Through unsupervised learning, we can identify latent patterns in the data and start to form groups based on these patterns. We can think of each of these variables in my data set as a data dimension. And rather than clustering directly on this existing data, the first step is to reduce or transform the data. And this approach filters out the less relevant features, and it increases the efficiency in problem solving. Then, using this reduced data, clustering algorithms are applied to start to identify patterns or groupings of similar data. So I'm showing some very preliminary and in-progress clustering that I've been working on over the past few weeks. Here we see cluster visualizations generated using a K-prototype algorithm that's applied to the reduced data. And this is an 8-cluster solution, which isn't necessarily the correct number of clusters. Again, this is work in progress. So when we present a plot like this, each dot represents a person in my data set. And keeping in mind that I'm starting with around 40 dimensions, as humans, we can't actually visualize this. So the clustering allocation, we then take, after the clustering allocation, we then reduce the data further into 2 dimensions and then plot this so that we can visually start to interpret what the clustering might look like. We can then look at who is in each of these clusters. So here I'm plotting, sharing plots for females and for males. And again, I'm sharing an 8-cluster solution, which isn't necessarily correct. But here what we can see is who's in each of those clusters using those same social determinant indicators that I used in that first objective. And recall that these reflect those with the most social disadvantage, the lowest income group, the least education. And we can start to look at the prevalence of social disadvantage by cluster membership. The unsupervised clusters reflect multiple dimensions of social risk within a single descriptive indicator, which is an advantage over the single risk factor and an advantage over the additive approaches that I've shared initially. But this is really a data-driven approach that requires a theoretical lens to the interpretation. There are, of course, some limitations to the approach, as there's no absolute truth. And this is an iterative process that really relies on the expert knowledge of the research team to identify how many clusters are appropriate and how to interpret the generated clustering. So briefly speak on the next steps of my research. The first being to complete the cluster-based sex-specific social risk measures that I've just shared briefly with you this afternoon. And then once these have generated, I then want to look at how the variation in social risk clustering, how it varies across Ontario health regions, just to understand how the population level social risk clusters may vary across the province. And finally, in my third objective, I will explore the association of these newly generated social risk clusters with multimorbidity to aid in the understanding of the combined impact of social determinants on multimorbidity risk. A few of the selected references that supported my work. And I'd like to thank my supervisor, Dr. Laura Rosella, and committee members and co-authors for their ongoing support and feedback, along with the members of the Population Health Analytics Lab. And I'd like to acknowledge the funding for this work, including CIHR, AI for Public Health, and the Novo Nordisk Network for Healthy Populations. Thank you.
Wow. Thank you, Ingrid, for giving us a very clear and succinct overview of this really impressive work. Congratulations on what you've done so far. It's very, very interesting, and you presented it very well. I'm going to open it up for some questions, and I'm actually going to ask your faculty advisor, Dr. Siddiqui, if you wanted to start, if you had questions or feedback for Ingrid.
Sure. Yeah. Ingrid, really fantastic work. I'm going to keep it short because you and I always have time to chit chat. But I think one thing that kind of occurred to me as you were presenting is what role your work plays in relation to the vast social determinants of health literature, in the sense that so much of that literature is theory driven. And it has opinions about social determinants in various ways. So about multiple social determinants. And over time, it'll be interesting to kind of figure out how your work kind of intervenes in different aspects of that literature. So yeah, congratulations on everything you've done so far. Let me open the floor. I see Haley.
Yeah, thank you. Ingrid, this was just phenomenal. Wow, I'm really blown away. So congratulations on the work that you've done so far. I do have a question. I'm someone who focuses more on chronic disease epidemiology, so on the outcome aspect of the multimorbidity, because I think you did a really nice job laying out why in the exposure side, it's not maybe a fulsome picture if you just do a checkbox, are you employed, not are you high income or not. But then on the outcome side, with the multimorbidity measure, 2+, you are considering all those things to be equal. And I think that potentially one could say that having something like a chronic disease like asthma could be entirely different from a chronic disease like COPD or heart failure. And so I wondered if you thought about on the outcome side, how these different chronic conditions, might impact someone's health, and, something like a Charlson Comorbidity Index or another weighted type of measure for the multimorbidity assessment.
Yeah, it's a great point. I was actually thinking about this, I don't know, 25 minutes ago, or just before starting the presentation, about like, what can I do, or what sort of comes next with looking at this generated measure, because it's such a crude and simplistic way of looking at it. And I think that's part of the problem generally in multimorbidity research as well, is that we still tend to gravitate towards these really simplistic 2 or more, but nobody, as I said, like nobody is consistent in what 2 or more measures are we talking about, or is it 3 or more? Is it like by body system parts? And where my head went as you started to ask the question, and where I was, thinking about this about an hour ago, is sort of like, well, how do the generated, the unsupervised clusters, do we start to see different patterns in what multimorbidity combinations are picked up, and what does that end up looking like? It's an interesting point on using some of the other indicators, and I think like definitely something that we should take back, or that I should discuss with my committee in more detail, about how am I capturing multimorbidity. I think in some ways, there's been a bit of an arc since I started to work on this, and when I first proposed it in 2021, and some, might be a good time for pause and reflection about like, should we change that? How should we change it? I think the other thing that's neat about it is that I actually I don't think it matters what that outcome is that you look at. We're going to start to see different things that come out with this exposure measure in this way. And so what I mean by that is, like, we could look at the individual chronic diseases, and that tells one story. We could look at a combination in at different life stages, and that's probably going to start to unpack a different story again. Yeah, sorry, that's a long answer, Haley, but thank you for your question.
Yeah, no, thanks for the answer.
Yeah, thank you, Haley, and Arjuman. So anyone else have any questions for Ingrid? so while people are thinking, I wanted to sort of expand on the issue of the outcome. I recognize that your focus is on that sort of concept of multimorbidity, where people have, chronic, like they have comorbidities, they have more than one problem. But I'm assuming that there's been literature to look at the potentially different effects for the different conditions within your multimorbidity outcome. Because, and I think this was alluded to exactly what Haley said, is like someone who had like asthma or COPD may have different clusters of risk factors than diabetes, right? So, or congestive heart failure. So I don't know if you're planning on, I know it's a different question, but whether you're planning on exploring that or whether it's been done by others or both.
I don't, certainly not with the exposure measure the way that I'm considering it. I haven't seen that done for. And I think, the first point is let's start with something simple and see how it works, and then see what comes next after that. Like if you look at maybe the early conversations that I had with Laura about what I wanted to do with creating this measure, we've really had to scale it back because of, it's baby steps in building up the story. It's not, jumping in where I want the story I want to tell. We need to make sure that, this is a coherent story that unfolds as it goes. And I do think, there is a lot of opportunity after the cluster is generated to then start to play around with what does that exposure measure look like, and how do we start to see various patterns, unfold.
Yeah, and I think that's you absolutely have the right approach. I'm just sort of throwing out, something else you could do afterwards potentially as a different, it's a different question. It's not the same question. I think having an understanding of those, those clusters of, for lack of a better word, of social risk factors or social predictors of having two or more conditions, I think is really useful for resource planning and et cetera, just and trying to and creating more tailored pathways for patients around but being very clear that these clusters are not, they don't differentiate between diabetes and COPD, for example. That would be, the only caveat there, right? So if somebody has diabetes and CHF versus COPD and CHF, your clusters are similar, but perhaps they wouldn't be if you looked more closely. Yeah, Laura.
Yeah, I was just going to say our lab has actually done differential social exposures and multimorbidity by condition, but not what Ingrid's done, which is like so that would be the next stage, right?
Right.
But just to say, to your point, Lorraine, when you do that, you definitely see the strongest social relationships with diabetes and COPD, for example, much stronger than other chronic conditions. So to some extent, you might expect the score that Ingrid's developing to be even stronger, specifically for diabetes plus comorbidities. That's what I would hypothesize based on the work that we've done, which is even simpler than what Ingrid started.
Yeah.
So I think that would be very interesting. And also just to say, there's been a lot of clustering work just for everyone's interest done on multimorbidity through lots of other groups. Walter's done a lot of work on this. And it's really interesting that diabetes is the most common, but after that, it's a bit random, to be honest, when you accumulate these, which comes first. Not completely random, but there is this constant, and it's an aging phenomenon. It's kind of interesting. I think when they started the work, they were thinking we'd find the clusters, but they're really hard to find in the outcomes. So just to add those couple context points.
Yeah.
That might be interesting.
No, that's great. And, I think we're out of time for questions. We want to give time for the next speaker, but I really amazing work, Ingrid. And I think, with this methodology and this, and I think you're really on the right track with helping to answer these questions. I mean, starting out with sort of a more, as you said, a simple measure, because certainly the methods are anything but simple. and then kind of digging in deeper. I think you've got the next 5 years laid out for you, my dear. It's wonderful work, and congratulations. Very well presented. Please join me in thanking Ingrid for a really nice presentation. So now I'm going to move on to our second speaker, Scarlett Rakowska. So Scarlett Rakowska is a doctoral student under the supervision of Dr. Matt Adams, with the faculty advisor for today's session, Dr. Jue Wang. Scarlett is a second-year PhD student in the Department of Geography, Geomatics, and Environment at the University of Toronto, Mississauga. And her research focuses on conducting geospatial techniques to explore the built environment and non-communicable diseases. Her research interests include urban health, greenness, geospatial analysis, and how they impact health diseases. So without further ado, please join me in welcoming Scarlett for her presentation. Go ahead, Scarlett.
Thank you for that introduction. Let me just make sure I can still see everyone. There we go. And can everyone hear me okay? Yes, great. Okay, so hello everyone. My name is Scarlett Rakowska. I'm a second-year PhD in the Department of Geography, Geomatics, and Environment at the University of Toronto. My research kind of takes a bit of a shift into more remote sensing, GIS kind of realm. So today I'll be talking about integrating LiDAR and satellite imagery to assess the relationship between types of green space and diabetes in Mississauga, Ontario. So I'll start off with a quick land acknowledgement as well. This project is based in Mississauga, so we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. And today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have this opportunity to work on this land. So I'll start off. So research indicates that green spaces play a vital role in our health and well-being. And this stems from our evolutionary need to connect with nature. So this suggests that we have this inherent desire to engage with natural environments. And numerous studies have shown that, sorry, am I sharing my screen right?
Yeah, everything is great.
Yeah, okay.
Yeah.
The green line just went away, so I wasn't sure.
We hear you and your screen looks great.
Perfect, thank you.
Thanks.
So numerous studies have shown that exposure to green spaces can significantly reduce stress, enhance mood, and improve physical health. And green spaces also offer several health benefits. They foster social cohesion by encouraging interactions that strengthen community bonds, leading to also better mental health. These areas also promote physical health, providing ideal settings for exercise, which helps reduce obesity and cardiovascular risks. And additionally, this vegetation in these green spaces also serves as a natural buffer, so filtering any harmful pollutants and reducing noise. And this is particularly important in urban areas where heat stress can be a concern. And together, all these factors kind of contribute to both mental and physical well-being. However, studying these green spaces is very complex, so they vary widely. So in terms of, let's say, parks, forests, and gardens, and each type can have different health effects. So this complexity makes accurate measurements and evaluation challenging. For example, a park full of trees may offer like different benefits than a flat grass field, for example. And then this brings us to the central motivation for this research. So not all green spaces provide equal value to health. So despite these differences, many green spaces are often assigned to same geospatial measurement values, such as common greenness indices, such as NDVI, which I'll talk about on the next slide. And then our hypothesis here is that the type, structure, and quality of green space, as measured by many more advanced technologies, have significant impacts on different health benefits. So now let's just explore some various techniques used to measure greenness. So each offering very unique perspectives on our green spaces. So first we have a vegetation indices such as NDVI, which is the Normalized Difference Vegetation Index. This widely used tool quantifies greenness by analyzing satellite imagery that then measures the light reflected during photosynthesis. So NDVI provides a straightforward estimate of vegetation density, making it an effective method for assessing green space around homes or neighborhoods in very large scale studies. It's consistent, it's easy to calculate, and it's capable of covering vast areas effectively. Next is any land use database, which categorizes area into different types of, for example, green spaces, built up areas, and water bodies. While these classifications do offer insights into the different land uses in study regions, they do not accurately reflect the actual presence of vegetation. So for example, a park could be designated as a green space, even if it has minimal greenery. And then this method does aid our understanding of green space, but it lacks the detail regarding the quality of vegetation. And then finally, we have distance matrix. So this would measure maybe how far a person lives from the nearest green space. While this approach does provide a general sense of access, it doesn't address the quality, size, or usability of that space. So for instance, proximity to a poorly maintained park may not offer significant health benefits. So here we have 3 examples of NDVI comparisons. So like I said, NDVI is kind of like a greenness index. So it ranges from -1 to 1. Anything above 0 and closer to 1 would be like dense vegetation. And then less than 0 would be anything either not vegetation or very low quality vegetation. So here we have 3 examples. It's very hard to tell what is what. So just by looking at these NDVI values. Here I was able to extract the values of specific points on the 3 regions. So on the left here, we have something about 0.86, so a pretty high to moderate NDVI value. The middle here, we have 0.78, so a bit lower. And then the one on the right is kind of, I have 2 examples, 0.85 and then 0.74. So just by looking at these NDVI values, we don't really know what's going on here. We don't really know what type of vegetation is here. Then by looking at the satellite imagery, so we can see that the left one looks like it's some sort of dense forest. The middle is a grass field. And then the right, we have a bit of a combination of a forest, grass field, and then even like a small creek. And then in terms of accessibility, the one on the left is actually it's a forest, but you can actually go into it. There's actually paths that allow you to walk through this forest. The middle one is an open field, very accessible for the public. And then the right one is actually just behind UTM. You have the forest, grass field, and then the creek. And then the forest, that was that 0.5 value. I don't know for sure, but it doesn't seem like it's too accessible to the public as opposed to that left forested area. So just by looking at these values, NDVI just kind of gives us values of greenness, but doesn't really tell us much about what's going on in the area. So the relationship between green space and health is very complex. So research indicates that not all green spaces are created equal. So for instance, a tree-filled park may provide different health benefits compared to a grass field. And then additionally, green spaces also foster social interactions and community cohesion, which enhances mental health well-being while reducing environmental stressors like heat and pollution. And then, however, access to quality green spaces is often inequitable. So particularly for lower socioeconomic groups who may actually benefit the most from these environments. And then this disparity emphasizes that there's a need for this to address inequality in green space access as a critical public health issue. So going back to our 3 examples, so now if we add LiDAR, so light detection and ranging, it's a groundbreaking technology that creates detailed 3D maps of trees and vegetation. So unlike traditional methods, LiDAR captures vital information about tree height, density, and overall structure, providing a deeper understanding of the green space. So for instance, by analyzing a LiDAR scan of tree canopies, we can actually differentiate between dense forests and sparse areas, such as grass fields, which can have varying health impacts. So while NDVI measures that vegetation density, integrating it with LiDAR would actually allow for a more comprehensive assessment of green space quality and function, ultimately enhancing our understanding of their role in public health. So again, we have our 3 examples. So on the left, the LiDAR, that yellow color is actually showing that the LiDAR points are higher. So you can tell that they're we have tree canopy in this region. The one in the middle, we just have that blue like flat land, and then the one on the right, we can actually see specific trees, and as well as that creek that we didn't really see with those NDVI values earlier. So this goes into my study. So this study is very preliminary. I don't have many results to show today, but the plan here is to assess the effectiveness of integrating satellite imagery and LiDAR for land classification, and then relating that to health. So the next steps here, so we have data integration classification, associating this to diabetes, and then comparing those results to NDVI. So just by going through my schematic here, satellite imagery, we have specific bands from the satellite imagery, which will then also create indices, grabbing that LiDAR data and creating something called a normalized digital surface model. So that will create the actual height of objects rather than just the top of an object minus the ground, which would give us the height. Conducting supervised classification, which would create that land use classification, and then associating to diabetes and then comparing results to NDVI. So a little bit more about these methods. The satellite imagery that I obtained is from August 2021 through the satellite scope seen at 3 meters spatial resolution. So like I said, bands from this satellite would be red, green, blue, near infrared, which would help differentiate between vegetation and not vegetation, coastal blue, which would help with the kind of like the difference between water and then land, a second green band, yellow and red edge, and then generating many greenness indices such as NDVI, which I mentioned earlier, NDWI, which is a water index, and then SABI, which is a soil index. And then integrating this with LiDAR data, which is at 0.2 meters point spacing, which is also from 2021, creating that difference DSM, so which would give us actual heights of objects, and then merging this with the 3 meters of satellite imagery. So far, this is what we have. So this is, I forgot to mention this earlier, but with the indices and everything, after then creating that supervised classification, I did it in different band combinations. So this band combination is basically all the bands and then all the indices together. So this was done using supervised classification using random forest. So on the right, we have the classification of all of Mississauga, and then on the left, I chose UTM just because I thought people would be familiar with this area. So the gray we have are buildings, and then that darker gray is like paved areas are roads, and then those different types of greens would be deciduous trees, coniferous trees, shrubs, grass, and even like a marsh wetland. And then we're able to also see some water from that creek. And then bare soil, which was a little bit kind of from the construction from UTM from 2021. And then, so then this gives us like a kind of clear look of what's going on in the area, especially with those different types of trees. And then this LiDAR data is actually able to differentiate between these types of green spaces. So a regular like satellite imagery might just see grass and trees as kind of the same, but because we have that LiDAR, we're able to tell that obviously trees are taller than grasslands. And then here we have an accuracy assessment. So this is just assessing to see how accurate that classification was. So like I mentioned earlier, I did different band combinations. So on the far left here, we have red, green, blue, near infrared, and then plus LiDAR, and then other bands plus LiDAR, and then just the indices plus LiDAR. And then on the right, we have all the bands plus LiDAR. So the one that like was the highest overall accuracy was using all the bands plus LiDAR, which was about 88% overall accuracy. And then so you can just see here by just adding LiDAR, let me get my little user here. Just by adding LiDAR, we can see that the overall accuracy, or not overall accuracy, the accuracy for each land type increased. So for example, coniferous trees, before adding LiDAR, we had 70% accuracy. And then once we added it, we had 90, for example. Same with grass and shrubs. It increased as soon as we added that LiDAR variable. And then in terms of variable importance, which is essentially how important each variable would be. What's interesting here is that for every band combination that did not include LiDAR, the near infrared was the most important. So essentially, it helped the machine learning create the classification the most. And then anything that did have LiDAR, that LiDAR variable was the most important, except for this band combination was the red edge. But overall, in that classification that I showed earlier, the LiDAR variable was the most important in the classification. And the next steps would be integrating this data with health outcomes. So I have access to diabetes data from ICES. So I plan to now determine the amount of types of green spaces in each census tract, and then assessing that relationship between classified land use and diabetes prevalence using regression analysis while controlling for socioeconomic factors. And then comparing these results with NDVI. So essentially seeing, is NDVI enough to associate to diabetes, or would this machine learning and supervised classification of different green spaces help us in understanding diabetes prevalence more in the city? So the comprehensive understanding of how land use contributes to chronic diseases is necessary for healthy communities, as Mississauga has one of the highest rates of diabetes in Ontario. So this research will provide evidence-based results to introduce policies, interventions, and practices to reduce the risk of diabetes in Mississauga, Ontario. Thank you.
Great. Oh, Scarlett, excellent work. Really, really nice pictures. Really great work. Very interesting. Thank you. And very well presented. Thank you so much, Charlotte. Sorry, Scarlett. Apologies. So now we have time for questions, and I'll start with Shui. If you want to launch with some questions for Scarlett.
Sure. Scarlett, really fantastic and clear presentation. You did a great job in showing the advance of the LiDAR integrated method, and it's really fancy stuff. Well, I will keep my question brief so that we will have more time for others, to give others a chance to ask you questions. Okay, so first thing is that it looks like the spatial analysis, the spatial scale of your analysis will be in census tract based, right? So I wonder how many census tracts are there in the Mississauga?
It was in the hundreds.
It was in hundreds, and how many variables will be used for the regression analysis, including all different kinds of the green space and also other confounding factors or control variables?
I haven't looked into the diabetes data or looked into what regression analysis to do yet. So, but I do plan on integrating possibly all the green types into a model, and then maybe also differentiating different green types. So for example, the coniferous trees in separate models.
So my point is that because there's only limited number of samples in your regression model, you said about 100 samples, that you probably have you won't be able to import a large number of variables in your regression model. So this could be a potentially thing that you need to consider. Okay. And another thing is about, I think I remember in one of the slides you mentioned that in the existing method, we won't be able to evaluate accessibility of the green space, right? And how will your method addressing these issues?
Yeah, I didn't mention it in the presentation, but I wanted to, I showed that image of the like the forested area, and I mentioned how one of them was accessible and one of them wasn't. I was thinking of integrating this with City of Mississauga data of parks, because usually that shapefile would be accessible parks. I haven't looked into this yet, but that's kind of an idea I might have into understanding what's accessible and what's not.
Okay, so do you mean that it will be additional variable to be integrated in your regression model?
Possibly, yeah.
Okay. All right. I guess I see Jillian has a question for you.
So that was great work, Scarlett. Really, really interesting from a technological perspective in terms of the type of analyses that you're able to do, and kind of what the future of this kind of work will look like. I was just thinking through it's really fascinating with green space, how it impacts health and the potential mediators. As you mentioned, there's, is it simply access to physical activity, those social interactions? There's obviously, mitigating the effects of urban heat islands and air pollution. And then there's really interesting stuff around stress and brain effects, which is really cool, which of course can contribute to diabetes and other adverse outcomes, and ties very nicely to the first talk. So I just wondered, like, I don't know a lot about this, but the types of green space, like your hypotheses around, which of these components is going to be the secret sauce in terms of chronic disease risk, like how do they differ in terms of these different effects, like in terms of stress, in terms of, physical activity, we kind of know we need to have trails, you need to have a place to go, but maybe stress and air pollution and other things that maybe us as, clinicians and health researchers don't always think about.
I think the main idea of the project, I think, is mainly understanding if NDVI is enough. Because I feel like a lot of papers are using NDVI as a greenness index, but I feel like it might not be enough. And I think we need to integrate other technologies and other types of techniques to see if specifically understanding what different types of green spaces are, if that's going to help understand more. But I would definitely want to integrate stress and air pollution and stuff like that.
But yeah, no, I think that's great. And I think it's a great question to ask, because, everyone's using NDVI, as you mentioned. We make assumptions. Oh, we'll just use whatever everyone else is using, and you'll see those differences. And I guess if you have the power to look at it, you'll see how those different components, like if we don't know, then it's great to do that exploratory work to understand, like, what is actually showing up as a signal in terms of predicting diabetes. And then you can actually do more hypothesis-driven work to see if this kind of combination is actually going to have a better effect in diabetes development and so on. I just wondered and it may be worth kind of looking and seeing, like, what is the other basic science kind of work tell us about. I would imagine trees are better than meadows for, taking pollutants out of the air, but, in terms of stress, like what is going to be kind of like, and how might they interact? And I think it's just more kind of maybe understanding that within the framework, but I think absolutely you're going to be able to see what aspects kind of stand out. And then I think just maybe building on Ju's point about that, thinking about your power and, this with built environment research, the smaller you can get to, the better. Like, can you get down to DA or other measures? I know the CT is available, but it's always kind of a trade-off. People share space, and maybe you don't have to get down too low in terms of like this block or that block, but just maybe think about that a bit more too. But I think it's really exciting work.
Thank you.
Thanks, Jillian. Do we have other questions for Scarlett from the audience? While people are thinking, Scarlett, I think just to, I think this, as everybody said, this is really great work, and I think it's going to be very useful for, both for researchers who are thinking about the connection between green space and disease risk, and also for policymakers around, where to, the justification for optimizing green space. But I'll pass it to Laura, who has her hand up. Go ahead, Laura.
Yeah, no, this is really great work. Very exciting. I'm just wondering, are there any, this is also, we're giving you future projects on this session. It seems like, any thoughts on actually going in person to these different green spaces to collect more like qualitative observations on how they look, and trying to put those things together? Yeah, because I think I like live in Mississauga my whole life, and I can just, they're so different, even though they kind of look the same from a measurement point of view. And I wonder if there's any opportunity to bring that in, what you would need to bring that type of data in.
Yeah, no, that was something that Matt and I definitely did discuss. I would like to go to those places and see what's there, and maybe even talk to the people that do use the spaces. Obviously, it is data from 2021, but the city hasn't changed too much. I did show like some examples of those 3 spaces, and the reason was because I live in Mississauga, so I know what they look like, and I know I can access these areas. But definitely, like you said, I would definitely like to go see what's there and actually take note of that.
Be great. And then just one more quick follow-up. Are any city officials, are you engaged with any city officials on these projects? Planning?
Not yet, no.
Yeah, I think they should be looking at your study.
Thank you.
Yeah, and you know, perhaps we can talk offline. I know Matt's involved with a couple of projects with the city, so you could probably look at where there might be some connections there. So yeah, I'm sure you could talk to Matt about that. Just one other point. I know that this is going to be really useful to look at the connection between diabetes prevalence and green space. But there's always this conundrum about, causality, right? So is it the fact that people who are at risk of diabetes, or sorry, have lower risk of diabetes or less likely to get diabetes, are also those who favor areas that are more green, or are the green spaces more difficult to access with people who have, social disadvantage to be able to move into? And therefore it's really like the social determinants of health that are driving the diabetes rather than the green space, right? Or it's the preference for green spaces that are, correlated. Anyway, just something to think about. These are not easy questions to answer, but thinking about how do you model for incidence versus prevalence? How do you, I know you're adjusting for social determinants of health, which will help, but just really being aware that there's going to be that, sort of that devil's advocate, sort of aspect of your work. People are going to be, are going, when people looking at your work. So just being ready to defend that. Joy, go ahead.
Yeah, I'm sorry. One last comment. This is actually not a question. So it's something adding up on top of others' comments, something you need to think about that because your study will be based on the census tract. It's more like neighborhood level studies. And you know that one of the potential criticized or challenges you may face is that people may say that where or how the quality of the green space in your neighborhood doesn't directly related to the exposures to the green space. For example, hiking lovers, you would travel and drive maybe half an hour away from their neighborhood to enjoy the nature and hiking. So something like that. So exposures to green space doesn't equal to the green space available in their neighborhood. So you may think about that.
Definitely, yeah. Thank you.
Great, thank you, Joy. So we have 1 minute left, and I think unless anyone else has any questions, I want to make sure we have time for people to get to their next meetings. So thank you very much, Scarlett, for a fantastic presentation. Please join me in thanking and congratulating her. You've done a great job, and I'm really looking forward to seeing your results and next steps for you. I think this is really important work. And I'd also like to thank Ingrid for a wonderful presentation as well, and wishing Ingrid the best of work, both of you the best of luck as you continue with your doctoral studies. So please thank you as well to the audience for your participation, and please join me as well in thanking our faculty advisors, Zhuai Wang and Arjuman Siddiqui, who had to step off early. So please ensure you complete today's evaluation for the session. The feedback is really important to us. Lydia will add the link in the chat pod, and we'll also be sending it directly. And just to let you know that our next Network for Healthy Populations virtual seminar is on November 18th, and we're so excited to have Dr. Laura Rosella speak at that next presentation, and we will send out more information shortly. So thank you, everyone, and wishing you a wonderful day.